everyone. Welcome to the main meeting of the Silicon Valley ACM SIGGRAPH. How many of you people are here at one of our events for the first time? Looks like we got about 8. That's about half. The rest, and four of the rest of us are officers here, and we got our speaker. But I wanted to tell you a little bit about our chapter. We are the Silicon Valley ACM chapter. We're a ACM professional chapter. We meet in Silicon Valley, thus the name Silicon Valley ACM SIGGRAPH. But what's SIGGRAPH? Well, we'll get to that. There is a conference called SIGGRAPH that is like a 24/7 immersion in computer graphics, and it's a very exciting week. And we'd like to try to extend that excitement throughout the rest of the year by having speakers talk locally, because not everybody can attend the conference. So we tend to focus on technology, but even if it isn't technology, it could be applications, but things that are new, fresh, state of the art. We're Silicon Valley after all. And of course, you know, you can do some networking and volunteering here. This is a class diagram of different organizations. There's multiple inheritance for the Silicon Valley ACM SIGGRAPH, which we'll get into, but the Association for Computing Machinery is the mother organization. It has a number of special interest groups, or SIGs, one of which is ACM SIGGRAPH, and it's called SIGGRAPH because it's a special interest group in graphics. ACM also has chapters, and there happens to be an ACM, a Bay Area ACM chapter here that isn't associated with any SIGs, but there are also SIG chapters too. And the Silicon Valley ACM SIGGRAPH chapter is one of those SIG chapters. There's another SIGGRAPH chapter in the Bay Area in San Francisco, and they have meetings monthly as well. We sometimes make it up there for the meetings, sometimes don't, but we tend to focus a little bit more on technology. They tend to focus a little bit more on production. So if you aren't on their list already, I suggest going to I guess siggraph.acm.org/chapters, or maybe chapters.siggraph, something like that. Or you can just look for SIGGRAPH chapters and sign up for the mailing list for San Francisco. As I mentioned, there's also this SIGGRAPH conference, which is not really part of SIGGRAPH, but it is. It's run by another organization. So it doesn't have the ACM in front of it, so it's separate, and that is coming up. So that's the class hierarchy of things. I don't know if you can read this, but these are some of the other SIGs. One of the ones that I want to point out was SIG-Chi, the special interest group in computer-human interfaces. Now, SIGGRAPH is a special interest group in graphics and interactive techniques, and SIG-Chi is, you know, interaction as well, human interaction. So there's a lot of back and forth on that. Yes, Carl?
And so there's a local chapter of ACHI, which is very active once a month, that has interesting meetings. So look for them.
You might find something else here, like logic, that you might want to join a group on. Again, this is a special interest group in computer graphics and interactive techniques. You can just type in acm.org or siggraph.org, or you could click on those QR codes if you like. We've got a website. There's a meetup, which you probably signed up for. That's how you found out about it. We have an email and a YouTube. We're broadcasting on YouTube right now, and we do archive our meetings, at least since we started the pandemic. We've been archiving them, so you can go see some of the older ones. There we go. So we'll meet our volunteers. The chair is not here right now. Where is he? You know?
Yeah.
Hawaii. I think he's in Hawaii. And Brent is the vice chair. He's over there. Carl is the treasurer.
Not in Hawaii.
No. Sharon is the secretary. And I'm a member at large, formerly chair, and other things too, but I need to get some of you guys involved and be officers, so I stepped away a little bit. That's what this place is for you, right there. So we are looking for other volunteers to help run these meetings, contacting speakers. Eventually, when we are doing the live and recorded, well, eventually we want to get back to where we take the speakers out for dinner beforehand and get a chance to engage with them in that way. So this is oh. Let me go back there. We do try to have meetings every month. Unfortunately, we don't have a June meeting set up yet, do we? Well, we will have one. Just watch Meetup for that. I mentioned the SIGGRAPH conference. This year, the conference is going to be held in July in Los Angeles. But about 8 years ago or something, they started an Asian SIGGRAPH to allow other people to attend in other parts of the world. And that's going to be held in the beginning of December in Kuala Lumpur. I'd go there. Malaysia, yeah. 2 years ago, I think it was, in Japan, and a lot of my colleagues went and they really loved it over there. So I may give it a try this time. So come join. You know what the registration is for SIGGRAPH? If you want a full registration, it's something like $8.95. For $2.95, you can get the full experience, I guess. Well, it's called experience. It gets you into everything but the technical paper productions.
Like the expo type thing.
And student discounts too. right?
Oh, there are student discounts, and also there is the exhibition only pass, which you can usually get for free. But otherwise it costs $25 or so. I keep looking at our speaker, Kalina, because she's on the executive committee of ACM SIGGRAPH. And let me tell you a little bit about her. She's going to be our speaker tonight. Kalina is a researcher at the intersection of computer graphics, data visualization, and human-centered computing. She spent a decade at the National Center for Supercomputing Applications, where she was the founding director of the Visualization Program Office and the director of the Advanced Visualization Lab. Kalina has also worked at the New York Times, Autodesk Research, and Apple. She's currently pursuing a PhD in graphics and visualization at the University of Utah, though this summer she's spending it at Apple. At the SIGGRAPH conference, Kalina has served as the Computer Animation Festival Director in 2023. She was the course chair in 2025, and she's currently a director on the executive committee. Please welcome our featured presenter for May, Kalina Borkiewicz.
Thank you. I'm just going to switch over to my other slide deck. Anyway, thank you everyone for your warm welcome and your patience. I'm going to be talking to you today about cinematic scientific visualization. But first, before I get into the details of that, just a little bit of an introduction about me and what I've been up to and how I got to where I am today. So a little timeline along the bottom. The one kind of constant since I began my graphics career in 2014 is that I've been involved in ACM SIGGRAPH in one capacity or another. As we mentioned, I'm currently a director on the executive committee. I was not that this whole time. That's just in the last year. But I've volunteered with lots of different programs on both the conference and organization committee, and I'm really happy to be speaking to a SIGGRAPH community here among you all. I did spend most of my career at the National Center for Supercomputing Applications, which is part of the University of Illinois at Urbana-Champaign. I started there as a research programmer, eventually worked my way up to director of a lab and also founding director of an entire program that oversaw all of the visualization efforts across multiple teams. So was really grateful to have had all of those opportunities. Did a lot of cool work there, and you'll be hearing a lot about that. 10 years is a long time, though, to be spending somewhere. So after a decade, I decided that it was time for a change. I left that job and went back to school. So I am currently pursuing a PhD at the University of Utah. Been doing that 2 and a bit years in. I've also spent a year at the New York Times on the graphics desk, was doing some sports journalism as well as political coverage, data visualizations, and graphics relating to just what was going on in the world at the time. I did a brief stint at Autodesk Research on the HCI visualization team, and just on Monday, I started working with Apple on the camera and photos team. But what I'm going to be talking about today is kind of the bulk of my career, which I spent at the NCSA, and I continue to do cinematic scientific visualization research at the University of Utah, but we'll be primarily talking about the work from that time. So the work that I had been doing and continue to is cinematic scientific visualization. I'm curious if anyone has heard that phrase before today. 2.5 people. Awesome. I've been trying to popularize it. But essentially what this means, how I've defined it, is in the space between kind of some other concepts. When you see scientific imagery, there's different forms that could take. One common form is scientific illustration, which here I'm showing a planetary collision created by artists at NASA. That's just, created by an artist. It's something from their imagination. We know that planets collide and we can imagine what that might look like. And here's an artist illustration of what that might be. On kind of the other side of a spectrum is data visualization. So this is also a planetary collision, but this has been calculated on supercomputers using the known laws of physics by scientists who do this type of research. And there's numerical values and data positions and temperatures and densities and all kinds of data points associated with this type of work.
But it's not quite as beautiful.
But it's not quite as beautiful. Typically, it's used for data analysis, for research purposes, for scientists just kind of trying to understand what's happening. And where cinematic scientific visualization is in between these two. So it is both art, but it is also scientifically accurate. So this image in the center is actually the exact same data set as the one on the right. It is a supercomputer simulation by Dr. Robin Knupp from the Southwest Research Institute, but it has been visualized for a general public audience. This was created for a documentary film in a planetarium full dome immersive context. So we took, a lot of time, put a lot of effort into making it beautiful and cinematic and understandable, but it is also entirely based on data. So creating this type of work requires a balance of science and art and technology. And the Advanced Visualization Lab team that I was part of and that I led was about half and half artists and programmers working together. And for every new project, we brought in scientists as well that were the experts in that work. And we created a lot of documentary films. Here's the ones that I personally had contributed to, but we also created a lot of work for museums, for social media, even for concert graphics, or just kind of any type of edutainment, as we call it, education plus entertainment. And I'm gonna show a brief demo reel showing some of that work. Thank you. That was not just my work, that's the work of an entire team. Props and credit to all of the folks involved in that. As you can probably imagine, creating this type of work involves a complex pipeline that involves, data processing and rendering, all the fun, typical computer graphics stuff, and then a lot of fancy science stuff. We created this to try to kind of explain that, but this is way too detailed to get into for a 1-hour talk. So I'm going to simplify this as saying creating these types of visualizations involves solving 3 types of problems: technical problems, design problems, and communication problems. And I'll dive into these one by one with some examples of what those look like. So starting with communication problems, these visualizations are often intended for a very wide age group. We target kids as young as 8 years old, all the way up through, I mean, not necessarily ending at 80. It's just nice to say 8 to 80. Has a nice ring to it. But, going down as low as 8 involves lots of challenges of how to communicate something in a way that's simple and understandable to a kid. Meanwhile, something that is also accurate and understandable to someone who has a PhD in that same topic. How do we make something make sense to both of those audiences? This is a comic that I love that I think demonstrates one of the challenges of communication perfectly. So here's someone at a podium saying there's an eye at the center of a hurricane. One person interprets it correctly, another thinks there's an eyeball in the middle of it, and the third thinks it's the letter I. Even when you think that you're saying something very clear, very succinct, very simple, people can have very different interpretations of that and take home the wrong kind of message. And this is something that we deal with and think about on a daily basis. So one of the projects that we worked on was visualizing the process of photosynthesis in a bacteria. And so I want to kind of walk us through this thought exercise of, okay, if we wanted to visualize photosynthesis, how would we do that? So, at a high level, first you think about, what are all of the steps? What happens? So a photon hits a chlorophyll gets excited, electrons are activated, stuff happens. I'm not going to go through the list. Let's start by looking at step 1. A photon hits a chlorophyll. This is the very first, most basic step of the process. Breaking that down even further, a photon, that is a unit of light. How do we represent that? If you look up a photon on Wikipedia, you'll see images like this. What the heck are we looking at? What does this mean? A photon is a quantum object that has wave-particle duality. There's lots of complexity around how it works, a lot of uncertainty around how it works. How do you explain something like this to an 8-year-old? Well, you really can't in all of the detail that you would find on Wikipedia, for example. So figuring out how to simplify without misleading or lying to your audience is a big challenge. Here are some snapshots of some tests we did of, how do we maybe show wave particle duality with something like a photon while trying to keep it simple. These were tests that we weren't quite happy with, but did a lot of iterating and talking to scientists about okay, how do we show photons hitting this bed of objects? One of the things that we kind of decided as a team was that, while accuracy is incredibly important, making something that's understandable is even more important than making something that's fully accurate. So I came up with this kind of hierarchy of needs for this type of visualization, where at the very bottom of the hierarchy, what is most important of all is that it's understandable. And sometimes, unfortunately, that does come at the cost of accuracy, like a photon. You just can't show that accurately. And then appealing is also incredibly important, but that cannot come before it being accurate or understanding. Cinematic visualization is known for being beautiful and for its visual appeal, but we really can't work on that or worry about that until we've achieved the 2 other building blocks that are in this hierarchy of needs. So when we're deciding on visualizing a data set, there's also a lot of different ways that it could be visualized. So here we're looking at 2 different styles of showing a tornado. On the left is a very abstract visualization that shows more of the inner workings of how the storm forms. On the right is a more photorealistic version that doesn't necessarily show you much about what's happening inside, but is something more like what you would see with your eyes. Maybe communicates more of an emotional message, you know, looks more frightening and ominous, whereas the one on the left looks more clinical and analytical. So there's a lot of thinking about the point of the visualization, the audience of the visualization, to make decisions as to how you even represent this, what it is that you actually want to communicate, what feelings you want to evoke, what you want to teach. Even though, you know, the same data set can be visualized these very different ways and get very different outcomes. Since all of these design decisions do make, you know, different kinds of sacrifices, you can show, you know, one thing at the expense of hiding another thing. We work very closely with the scientists who are actually experts in these fields because, you know, my background is computer science. I am not an expert in photosynthesis or tornadoes or astronomy. So I'm not going to just decide that something looks pretty and do that. The scientists are the ones that really keep us on our toes and make sure that we are conveying their work appropriately. But talking to scientists isn't enough. We also need to talk to our audiences and understand how they are interpreting the visuals. Even if the scientist okays it and says, yes, this is perfectly accurate, this is great, you might still show it to an audience and they might still be confused. So audience testing and doing audience research is also very important. One of the things that we found out a few years ago is that sometimes our audiences were confused about what they were looking at. Like, is it real video that was recorded with a camera? Is it something created just by an artist and made up, or data visualization? People weren't necessarily understanding the difference between those things. So, you know, getting to research this with our audiences helps us figure out how to address those challenges. We've done surveys showing our visualizations to audiences and getting feedback on how they feel about the visuals, what they're confused by. We've done focus groups. Here's a Zoom call where early in the design process, here we were kind of testing different colors and showing it to people and being like, well, what feelings does this evoke? Which one do you prefer? We don't always go into this level of detail with everything that we do, but when we do have the opportunity to, it's very useful and valuable. So the next type of challenge that I want to cover is design. So what is it that actually makes a data visualization cinematic? No matter what type of visualization you're creating, whether it's a bar chart or something cinematic like what I've been showing, there are some common types of questions that you have to think about, like how will you represent the data? Even if it's simple, like, well, a bar chart or a pie chart, you know, always, this is something that's common across all visualization. What aspects of the data do you want to highlight? Because you can't show everything all at once. What colors will you use? There's a whole number of standard questions that all visualizations think about. Cinematic visualization design requires all of that, plus many, many others. So thinking more along the lines of cinematography and film and scene development and design. So how do you put the elements in a scene together? How do you choreograph the camera through that 3D scene? Thinking about the composition in the frame, so things more typically associated with art and design and photography and cinematography. So as a concrete example, here is a visualization that is not cinematic. This is a kind of traditional visualization created by scientists that is showing an organelle called a chromatophore, not that it matters what it's called. And this was from that photosynthesis project I was talking about. This is part of a bacteria that actually photosynthesizes, turns light into energy. And you can kind of see them trying to explain that process. You see kind of this ray of light and things bouncing around. So we wanted to use the same data and tell the same story of photosynthesis, but to make it cinematic and exciting and immersive and understandable to audiences of all ages. So here is how we did that. If I can progress the slide. So we started out by creating a context. Just showing this ball floating on a white background was not very helpful or useful. So we organized these chromatophore objects into the shapes of the bacteria that they're found in, which are a more familiar type of shape. We zoom into that bacteria and start to show more and more detail as the camera gets closer. Once we get close enough, we actually fade into an X-ray view to look inside of this chromatophore object and see even more complexity. So we don't just show everything at once, we reveal more information as the viewer gets a chance to become more familiar with their surroundings and their environment. And finally, after all of that, we do eventually see a beam of light hit the chromatophore and the process of photosynthesis actually begins, and then the camera follows the process all the way through. I'm not going to show the whole video because it's quite long, but that introduction is an incredibly important aspect, setting up the scene, walking the audience through what they're going to see, and building up complexity over time. Next slide. I mentioned photography and cinematography is very important, so we borrow a lot of techniques from that space. One is the rule of thirds. Anyone here a photographer? Nice, you're all very familiar with this then. So for people not familiar with photography, if you looked at a visualization like this, you might see kind of like a third here is just black. That's a waste of space. Why are we doing that? Actually, it's because when you align the point of interest along the 1/3 and 2/3 lines of an image, that is more pleasing to our human eye for some reason. So here, this is a visualization showing the Earth and solar plasma engulfing it, and we place the Earth at the intersection of these lines to make this image more aesthetically pleasing. One thing that is very uncommon in other types of data visualization is putting the camera inside the data box. A lot of times for more traditional visualization styles, you'll see something like what I'm showing on the right. We call that universe in a box, where you kind of look at the data from the outside and you kind of analyze it, but we don't like to do that. We like to put the audience directly inside the box in the middle of the action, as close and as personal as we can get it to the audience. We try to avoid showing the edges of the box. We want it to feel immersive. We want it to feel like you're there. A lot of times we do create shows for planetarium dome environments that are literally immersive, but even for a flat screen design, we don't like to show the edges of the box. It's distracting. To kids, it's even confusing. Like, what do you mean? Is there no universe over there? So that's a very important design aspect. There's a poster falling in the room right now, so apologies that we're all laughing if you hear that online. So another thing that we do is camera lens effects. We get some flack from the broader visualization community for this because we're degrading the image. We're blurring it, we're making it worse. Why would we do that? Well, we do that because it makes it more cinematic. It makes it more beautiful. Data analysis is not the point. Perfect accuracy is not the point. The emotional appeal is increased by making it worse in a way. We're degrading the image by doing these things, but it does add to the emotion to it. Lighting can add a dramatic flair to data. So here we're doing a grand reveal of these hurricane features on the Earth. Starting on the dark side, this is a fun thing that typically in Earth shots, you'll like to see that. There's a really cool rim effect around. So lighting is a really powerful tool. And the final aspect I want to talk about is that we provide context to data. So here is a data set that I'm showing that's visualized without any context. This is just one simulation from one team of scientists that if we just showed it on its own, would look like this. You could probably guess what it is, but maybe you can't. I'll take any guesses. Does anyone want to say what they think this is? Yes. The sun. Yes, you got it. But, it doesn't really look like our sun or what you would expect it to be. It's an orange ball, so yeah, sun-like, but I don't know, looks kind of weird. This is actually the inside of the sun. So showing the inside of the sun on its own is kind of a little weird. So what we did is wrapped the inside with an outside. So this is the shot that we created from it. We start out flying over the surface of the sun, then we dive underneath that surface and then show that data set. So again, just a kind of a brief introduction, set the scene, make it a little bit more familiar for the audience. But combining data sets introduces challenges. These are different data sets that we put together to create this shot. We didn't just artistically create all of these other aspects. So here's a screenshot from later in that video where we have an X-ray view into the interior of the sun. And I'll break this down to talk about what went into combining these data sets. So one data set that we had was a solar surface convection from a scientist named Matthias Frempel. And we rendered these kind of spikes to show where those areas are. That same scientist had this simulation of the sun's surface, which does have these continent-sized nodes on it. And the way that that data actually came to us was as a series of black and white rectangular images like this. To cover the whole sun, we tiled that image, playing each tile at a different point in time, so that it wouldn't just look like repeating tiles, and we blended between the edges as much as possible, so that that wouldn't be visible and distracting. Then we created that X-ray view. Around the rim of the sun, we used photographic time-lapse imagery from NASA's Solar Dynamics Observatory. So that's actual video from our sun. The background, now there's like white points that are kind of dim on the screen, but we put it into the correct context. That's a photographic sky mosaic from Axel Mellinger, another scientist. And finally, we put the actual inside into the interior. But this also took a few steps. So the data that we actually got from the scientists looked like this. They had pointed out that a very important feature in this data set was what they called bananas, because you can see these kind of like banana shapes in the original. And these bananas spin as they kind of move around the sun. They also kind of spin around their own axes, which you couldn't actually tell in the original, the data that they gave us. So we added these kind of visual streamers around each of the bananas so that you can really tell that rotating motion. So we added that derivative data and combined that, put all of that together to create this final shot. So we move on to technical challenges. Big data was a kind of a hot word a few years ago, but even though you don't hear about it as much anymore, still a thing, and it keeps getting bigger. What I'm showing here is the Ruth, they changed the name. It used to be the LSST, now it's the Ruth something observatory. Anyway, it produces 20 terabytes of data every single night. And this is data that needs to be processed and visualized and analyzed. And that's the scale of data that we work with nowadays. This is a data set from a visualization that we worked on a few years ago of Arctic elevation. So this covered 1/6 of the entire globe at 2-meter resolution and was a 200 terabyte data set. It took the scientists 1.5 billion hours on the Blue Water supercomputer to process and assemble this data set. We did not work with the entire data set. We worked with a 45 terabyte subset, so still not tiny, but not quite that large, not taking credit for all of that. And just rendering this data took 110,000 hours on the Blue Water's supercomputer as well. So the size of the data isn't the only problem. Data is also always messy, especially data that comes from the real world. So this is a data set that was collected by satellites that go over the Arctic, take photographs, collect measurements, and reconstruct them. And a problem with satellite data is that clouds often get in the way between the satellite that's collecting it and the Earth, where they're trying to actually take these measurements. So along the top, you see these kind of messy patches popping on. That's when clouds got in between the sensor, and that made it very difficult to work with. We had to figure out how to remove those and clean them. Our very first kind of draft of a visualization where we just took the data and tried to visualize it. Here's like an island where these giant spikes are where we're trying to reconstruct height, but there were clouds in the way, so this is what we got. Clearly not something you could work with, put in a documentary, can't really show this to anybody. It's just absolutely terrible. So We had to create a lot of systems and pipelines and even wrote a machine learning paper for doing some automatic cloud masking removal in this massive data set to clean it, smooth it out, and that same island, we were able to get to look this clean without any of those cloud artifacts. So even just, this data processing step, which is what you need to do before you can begin the process of visualization, is a massive undertaking. I have a brief video that talks about some of the behind the scenes of creating some visualizations for this documentary film.
Here's what went into making a piece of Atlas of a Changing Earth. We built on the results of the Arctic DEM survey project. That survey used high-resolution satellite imagery, hundreds of thousands of observations spanning several years, and measured the Earth's shape in fine detail, covering all the land north of 60 degrees latitude. Transforming that imagery into this mapped dataset of Earth's topography required millions of hours of Blue Water's supercomputer processing. Satellite observations were in strips, a few kilometers long. Throughout the survey, many areas were observed on dozens of occasions, revealing how Earth's topography changes with time. This shot from Atlas of a Changing Earth animates the multi-year Arctic DEM survey in the context of a realistic-looking Earth. The visualization incorporates seasonal changes in Earth's appearance. We created it in layers. On the ocean is a climate model simulation of sea ice coverage. To design the unbroken animation path around the world and into Vavilov, we used AVL's interactive Virtual Director software. Virtual Director shows a simplified preview of the scene in the correct 3D location. Final rendered elements fit right in. Datasets, camera paths, and so on are brought into the commercial software tool Houdini from Side Effects. Its node-based architecture supports a mix of programmable and interactive design. The DEM survey data shows exquisite detail, but contains many artifacts, thanks especially to clouds. Seen in a 3D landscape, every defect becomes even more prominent. Lots of manual work went into cleaning the raw survey data, masking out clouds and aligning strips with each other. The DEM data was observed at discrete times at irregular intervals, days or months apart. To give the sense of continuous motion, we used morphing interpolation in Nuke on the high spatial frequency ripples in the collapsing Vavilov ice to create three-dimensional evolving topography. Here's what went into that. Flat version of the landscape, we add the time-interpolated topographic relief, and use Landsat optical imagery to provide color. It too is interpolated over time. Over wintertime darkness, we again alter the landscape color and lighting, and the sky, to suggest dim twilight. As springtime returns, so does Landsat imagery. The sun's very low as spring begins, so the early Landsat images are tinged pink with sunrise.
So many challenges, as you can start to get the sense of. Another one that wasn't explicitly mentioned, but was also part of this project is large changes in scale. So a lot of times when working with physical sciences, things are interacting across vastly different spatial scales and time scales. So for example, one visualization that we created was the seamless camera move that started out looking at the Earth, zoomed out to look at the solar system, continued zooming to look at the Milky Way, and it ended up looking at the entire observable universe. No cuts, no breaks, one camera move. Things like this are very challenging. You know, there's not one data set that covers all of that scale. So figuring out how to properly align things, avoiding floating point errors, you know, all kinds of challenges in putting together these data sets and actually being able to render them. I don't know why my thing stopped working, but okay. Another challenge is time is often not linear in data sets. It's a very confusing statement. What do I mean by that? You know, time moves like the bar in red along the top, but when scientists are either capturing data or collecting data or simulating data, it's often very large and very inefficient to capture it at regular time intervals. So when something interesting is happening, they'll take more snapshots. When nothing interesting is happening, they'll take fewer snapshots. So you end up with time bars that kind of look something more like this. You know, here something interesting was happening, lots of data there. Something interesting here, but not much here. So working with this type of data is also challenging temporally. So an example, I don't know why this stopped working.
Don't seem to be getting the
Oh.
pictures on the web either. It's, I don't know whether we're still on
Oh,
Zoom.
okay. Technical difficulties. We'll jump out.
Oh, there we
That's
go.
better.
What are you seeing online now?
I see you. I'm looking at Zoom and you've got the background there. So
Is that working?
there, that's working now. Good.
Okay. Excellent.
And YouTube will be following in a minute. There we go.
So with the example of time not being linear, here is a very simple example of that. So simple means easier to explain. This is a data set of a planetary collision, and you know, without us having really done any design, just kind of the raw data shown as points, you might notice that it starts out moving more slowly and then seems to speed up halfway through. So in this case, we just had two different time scales, not, you know, going up and down like in my previous slide. But before I explain what's going on, let me show you what the final visualization from this data looked like. If I can move my slide. Okay, so here we have added textures to the planets. We've added lighting from the position of the sun. We've added a background of stars. We used the data that was associated with each point to determine, based on the density and the temperature and the material type, whether each particle should be a solid, liquid, or a gas. If it was hot enough to be a liquid or a gas, we also made it emissive to light up, and you know, the light caused shadows and lit up the other points. You know, lots of changes to this from the previous slide. But obviously we also slowed this way down. We retimed it. I think we slowed it down by a factor of 20 in addition to just kind of the retiming it. Because, you know, this is a massive, large astronomical phenomenon. You don't want to just see it over in a second. You know, you want to convey the massive size of these objects and space and scale, and kind of convey a bit more awe and wonder, and moving a bit more slowly, getting the camera closer, designing kind of a more exciting camera move rather than just watching it from, you know, a top-down angle is interesting. What I love about this part is that I called this part getting whacked in the face, because this arm is about to just like kind of go right above us. This was created for a dome environment where if you imagine it kind of wrapped all around, you would actually kind of like went above the audience. Very dramatic, very exciting. Again, you know, we try to get the audience to really feel emotions while watching this stuff. So back to the timing thing. What's going on in this data set is that time is moving at just two different rates. So this particular scientist was more interested in studying the initial impact of these two planets, so she collected more data there, which is why that moves more slowly. She was a bit less interested in what happened later, so there's less data there. So whether it's kind of a simple change like this or something more complicated, there's many different methods that work differently for different types of data. In this case, advection interpolation is what we used, where for every single point, we advect it both forward and backward in time and figure out where it would be in between those. So that is how we slowed it down and retimed it. Yet another technical challenge is that data is often represented in all kinds of complex coordinate systems. Even a data set as simple as our planet with latitude and longitude can be represented all these different ways and more. Some of these might not be familiar to you, but maybe you've seen, you know, kind of a rectangular kind of map, square-like map. Maybe you've seen one of these. Turns out there's dozens of ways of representing even our Earth, as simple as it is. For more complex data, you might imagine, there's also very complex and varying coordinate systems that data can be represented in. Here are some of the weirder ones that I've come across. You know, not all just simple grids or simple triangles or what have you. Scientists like to get very creative because these are very large, so they want to be as efficient as possible. A lot of custom data formats that they create for this stuff. There's also no single software that does this kind of work. You might be familiar with, you know, some categories of this. Visual effects software does kind of half of what we want. That makes it easy to do the artistic side of things, you know, designing camera, making it look pretty. Scientific software doesn't really make things look pretty, but it does understand the complex data formats that we're working with. And there's a lot of custom software development that happens as well. Some of the custom tools developed by the AVL include this pre-visualization tool that is open source called PartyView, which we always used to kind of start the process. Working with these large data sets, we wanted a way to preview them interactively, downsample it, just kind of get a sense for what's going on. PartyView is the tool that we used to do that. We use that in conjunction with Virtual Director, which is an in-house tool for camera choreography, where we use a Space Pilot, which is kind of like a joystick 3D mouse type controller, to literally fly around the data and record a camera path. So here's an example of what that looks like for this planetary collision example. So we start by looking through the camera's eye, but then we can jump off of the camera path, and we can see that, you know, line is the camera, points being keyframes that we can go in and edit one by one, turn on a television view and really refine exactly what it's looking at and what that looks like. So this is a really kind of cool and unique tool in that it lets us perform a camera move rather than just kind of algorithmically defining it, which lets us kind of react to things a bit more naturally. Something that I think is really cool and I haven't really seen other places do. The video that I showed earlier mentioned that Houdini is a main tool that the AVL uses. Maya is also popular, but Houdini is becoming kind of the main one used in this industry. But there are other visual effects tools as well, but this is the one that I'll talk about since that's what I primarily have experience with. When I was a programmer in the team, one of my main jobs was creating C++ plugins to kind of extend the functionality of Houdini and do a lot of programming just to get the data working with this tool. So here's a tornado being run into the software and what that tornado eventually got rendered as. A problem with working in Houdini or other visual effects software is kind of what I alluded to earlier, that the data formats are very complicated. So that particular tornado that I just showed came in a stretched grid like the one on the right here. But Houdini only understands volumetric data that looks like this. So in the case of the tornado, where the actual funnel of the tornado was, there was, you know, a lot more data being collected. So finer resolution, where there were just kind of boring clouds in the distance, we didn't need as much. So that was had larger cells. That's kind of a common thing that you see in this type of data, where there's areas with more resolution, areas with less resolution, but that could look very different. So here is a different type of data representation that also has different types of resolution. Here is yet a different one. Data could be spherical or cylindrical or any other kind of format. So if we want this data to work with a tool like Houdini, sampling the data is kind of the main way to solve that problem. And choosing the right level of sampling is also a challenge. So you don't necessarily want to choose the finest resolution, because then that ends up having extremely unreasonable file sizes. But you don't want to choose, you know, a too big of a resolution, because the interesting stuff is happening where the small things are. So there's a balance there, and I'll kind of return to this a little bit later into how we solve this problem. But There is a different solution as well that a lot of other teams use using different software. You know, we're not tied to Houdini. I did mention this other category of scientific software. One tool that we used for a project called Solar Superstorms was a scientific tool called YT. I don't think it stands for anything, which is strange, but it does a really good job of understanding complicated data formats. So this kind of multi-resolution nested grid format that I showed a couple slides ago is actually how this data was represented, called adaptive mesh refinement, or AMR. Houdini just would not, but YT just natively understands that. Just load it in, you're done, bam. I mean, it doesn't just come out looking like that, but the data reading part is extremely straightforward. Scientific tools also have a lot of built-in tools that are useful for science things. So something that we often do is create streamlines through data to kind of show the flow of things. So with YT, it took 2 lines of Python code to create these streamlines through this data set that we rendered. So that makes that very easy. Could be done in Houdini as well, but might take, you know, a day of setting up nodes and networks and whatnot. So much easier with scientific tools. These scientific tools are often also set up to run on supercomputers. That's where scientists do a lot of their data processing and simulation. They do tend to be open source, unlike Houdini, which, you know, you don't really have a lot of insight into how things are working or ability to change. But YT in particular doesn't have a graphical user interface. So we did use this for an entire project. Put a lot more work on the programmers on the team rather than the artists. We had to create a lot more tools that we had to kind of move back and forth between visual and terminal and Python code. We had to kind of just do a lot more guess and check type of work. Obviously not ideal for quickly iterating. So pros and cons to both types of things. Another challenge with most scientific software is that it kind of tends to focus on one type of data. So YT in particular works great for volumetric data, but if you wanted to show something that is a combination of volumetric data with surface data or you know, other things combined, it isn't able to do that. And a lot of scientific tools kind of just do one type of thing. So a lot of what we did was customizing these tools. So when we were working with YT and Houdini together, they kind of have these very complementary strengths. We want something that ideally does, you know, kind of everything on this table. YT did exactly half of it. Houdini did exactly the other half. So we actually created a middleware that we called ytini. That let us, you know, didn't check all of the boxes, but let us use YT as a data reader within Houdini that did a lot of kind of data conversion between formats behind the scenes that let us continue to do our work in Houdini, but leveraged a lot of the features of YT. And ytini is open source as well, although Houdini isn't. But you can check that out at ytini.com. So here's an example of kind of an early attempt of trying to do some adaptive mesh refinement, so complicated grid data directly in Houdini and then with ytini. So kind of much more clean without seeing these grid artifacts in the data. So that covers the 3 types of challenges that I wanted to cover today. And I did talk a lot about the, you know, what we do and how we do it, but I haven't really covered the why. So I want to just take a few minutes of that. And the cop-out answer is that a picture is worth 1,000 words. We've all heard that a million times, but I don't know if you've seen 1,000 words before. So that's what that looks like. You know, I do agree with that. That is true, but kind of a cheesy answer. A better answer is the impact that this work actually has. Science is extremely important. Scientific research is the backbone of our society, I would argue. But most scientific research doesn't really make it past scientists. Scientists tend to just publish research papers that are only read by, you know, a small community themselves. If a paper has 1,000 citations, it's like renowned. That is amazing. But according to Wikipedia, only 0.026% of papers have 1,000 citations. So science doesn't typically reach a lot of people. Something like museums, on the other hand, here's the Museum of Science and Industry in Chicago reaches 1.5 million people every single year. So that is a way to get science to lots of people, to have, much larger impact. And how do we reach these museums? By creating these types of visualizations. So the Museum of Science and Industry in Chicago actually has a permanent exhibit that's showing one of these visualizations of the tornado that I showed in an earlier slide, together with an interactive booth where they can learn more. So that's a really cool thing. This is quite an old visualization actually, but it is still there. These visualizations, I have mixed feelings about this, but they have a very long lifespan. So there's a film that the AVL team worked on, Black Holes: The Other Side of Infinity, that was released in 2007, almost 20 years ago, and it is still playing in theaters. I looked it up. It's actually playing at the De Anza Planetarium here in Cupertino today, tomorrow. You could go see it right now. 20-year-old film, still being shown every day to people all around the world. The graphics have aged. I maybe wouldn't recommend seeing it if you're into graphics, but it's still educating children, still having an impact. Go see our newer films, but these last such a surprisingly long time. They reach people all over the world. Solar Superstorms, in just the 2 years after its release, got translated into all of these languages. I believe there's 10 of them. Also really cool. We often create these for like a specific film or museum or what have you, but they make their way to social media. They get shared many different ways. So here's one of our visualizations on social media with 3.4 million views. We didn't create it for YouTube, but it ends up all over the place and reaches millions of people in museums, millions of people on YouTube, millions of people on Reddit. Things pop up on Reddit all the time that I've worked on, and it is infuriating. A lot of times it gets credited to NASA, as it does here. It's by NCSA, it's one letter off, but I guess NASA sounds cooler. But anyway, yeah, it does show up. Also randomly find our work in movies, random places. So here behind, I forget this actress's name, in the movie Annie, nothing to do with science. They used one of our visualizations as kind of just like a science-y background. So it's just so cool to see this stuff out there. But in addition to entertainment, we've also had an impact on policy. There was a vote about funding space weather research, and our film, Solar Superstorms, was shown to members of Congress before that vote. And I'm not going to take all of the credit for it, but the bill passed unanimously. And, we talk about reaching broad audiences and the general public. That doesn't just include the 8-year-olds that I've been talking about. It also includes policymakers and people that make decisions and people that learn this and then make impact and change in the world. The 80-year-olds, exactly. So kind of on the last closing note, I've been focusing very heavily on, cinematic scientific visualization because that's where I've spent most of my career doing. But I want to get ahead of the question of like, wait, what does this have to do with the other stuff that I've done? Working at, is Apple Autodesk and the New York Times doing cinematic visualization? No, not exactly. But kind of the thread that connects all of this and the broader research questions that I'm interested in is, how do you take complex information and make it not only easy to understand, but also enjoyable to people that aren't experts, to general audiences? The way that my husband actually described this is making information not only digestible, but also tasty. And I love that. Digestible and tasty. So that's what I do. And I think that's a much more universal problem than just cinematic science visualization. And I'm looking forward to the next chapter where I'll be able to solve more of those interesting problems. So thank you for your time. I'll take any questions if you have them.
And if you're on the web, you can type in the Q&A, we're monitoring it.
Yes.
How does when you said 1.5 billion hours, how does that work?
So the question, repeating for the people online, I said that it took 1.5 billion hours on a supercomputer to process some data. How does that work? So that's not in real time, 1.5 billion hours. I looked this up once, that's like 30 some years or something. So it wasn't literally that amount of time. Supercomputer is thousands of smaller computers. So each of those computers spent, I don't know, a month or two. But a month or two times however many computers it is comes out to that many hours. So that's how you calculate and count up time on a supercomputer. So it's not literally taking that much time, but if you were running it on your computer, that's how long it would have taken. But yeah, that's what that meant.
Do you do the voiceover for these videos?
The question is if I or we do the voiceover for the videos. No. Well, I did once, but just for a YouTube version of the video. We typically hire like celebrity narrators, especially for the larger documentary productions. So we've had Benedict Cumberbatch and Jennifer Lawrence and, fancy narrator people do a lot of that work.
Okay, last one. Do you find yourself getting a lot of business for medical things? Like I can see this being helpful for people in physical chemistry or biology.
So the question was, do we get a lot of people from the medical industry that want this type of work? Yes and no. So my team or the AVL team primarily specializes in astronomy. You might have seen a lot of that. So we typically get that type of work. This type of cinematic visualization is very popular in the medical field. There's a lot of people doing that work. I am not one of them, but it is a common area. Yeah. Yes.
I have a question about the data processing itself. I know you talked about like artifacts that creep into the data that need to be removed. Data is not like structured in the way. Like, what's the main challenge that you face when you see this data? Like, is it always messy, or are they mostly standard? And then it's like, how do you deal with them?
So the question is, what is the biggest challenge when dealing with data? Like, is it always messy or standards, or kind of what is going on? So the biggest challenge is that no two data sets are the same. So I had been doing this work for 10 years and only came across the same data format twice. Every other project that I've ever done was an entirely new data format, entirely different problems, entirely different challenges. So that is what made the work fun and interesting. I never got bored, but it was also just, you can't just solve a problem once and then be done with it and move on to the next thing. You always have to kind of keep resolving it for a different use case, which is a little frustrating. Yeah.
I can imagine merging different data sets captured at different periods of different times of the day or different seasons. Is there anything that how do you do that and make things match up?
So the question is how to collect different data sets and make them match up. So
like you were it was taking stripes over the planets and
yeah, so my team had nothing to do with the data collection. We would always work with scientists that gave us that data, and then we figured out how to put it together and how to communicate it and design it and visualize it. I wish that I could just tell the scientists, like, just do it this way. Let's all agree, please do it this way. But that's not how it works. Everyone does it their own way, and then it becomes our problem to figure out how to put it together. But because we're always working with different types of sciences too, like, right, there's biology and there's astronomy and there's planetary science. They're not going to agree, like every scientist in the world across field isn't going to do things a certain way just to make my life easier. So while I complain about it, I don't expect them to change their ways. They're doing what they need to do, and we can solve those problems.
How long did it take you to make the ytini?
That was the question was how long did it take to make ytini? And that was an ongoing project that we kept adding features to as we were doing more stuff, but I guess maybe I'd say 6 months to like get a first version out, and then we kept updating it for maybe like 3 years as we were just adding more features. We started out by just doing it for ourselves, and then we were like, well, this could actually be useful for other people too. So we put it out there. Yes.
Yeah, my question is about not the scientific data that we're collecting. We're dealing with huge volumes of data and accuracy and everything. But I'm looking at publicly available data and make sense of it through visualization. And especially when generative AI and cognitive labor, so to say, is high, but the techniques to visualize that kind of data in an understandable, digestible, adding to what you said is not digestible, but also basic, so that that plenty of public data can be understood by people. So, is there any part or a resource or book that you could, or anything that you could point to, which talks more or treats this as a principle rather than a one-time thing?
So the question is, are there resources or principles I can point to that are kind of more generalized or generalizable rather than one-off things? So there are very many principles and books for kind of more traditional visualization, or, well, especially for like charts, infinite resources for that. More traditional scientific visualization as well. In terms of cinematic visualization, public-facing stuff in particular, I'm not aware of many resources aside from the things that my team has created. As I mentioned, we were at the university, they are, sorry, I'm still used to saying like we. Anyway, at the University of Illinois, so like education was a part of it. When I was there, a couple of colleagues and I actually created a Coursera class about how to create this type of work, and that's publicly available. It's a 4-week course. It's called, what is it called? Well, look up my name and Coursera. So that's a resource. If you use Houdini, there's also a couple Houdini school. There's like a website, houdini.school, courses, one that I've taught, and 2 other people have created these like modules for working with scientific data, specifically in that software and visualizing it. So that Coursera class, the Coursera class is free. The Houdini school classes do cost money. I think they're like $45 a class. So those are the things that I'm aware of. Yes.
Well, that's the AI question. So how do you see AI enhancing the future? Is it interpolation aspects or visualization, to really how to like pull something out of something? What do you see?
So the question is, what is the future of AI regarding this field? So that's part of what I'm studying with my PhD studies right now. I mean, there's obviously everybody is researching AI in every field right now, but I'll just speak to, cinematic visualization and my research in particular. I just submitted a paper to IEEE Viz a couple weeks ago, where I studied perceptions of visualization experts and scientists around using AI for visualization enhancement. The study was like, the premise was if scientists create like a very basic, not cinematic visualization, and then had the opportunity to use AI to enhance it, turn it into something more beautiful and cinematic, suitable for public. First of all, like, how would they feel about that? And the answer is unsurprisingly very negative. But also, what types of guardrails would they require in order to make them more comfortable? So what types of changes are and are not okay for an AI to do? So thinking about all of the things that it takes to take a normal traditional visualization and turn it into something cinematic, there's color and there's camera position and there's, infinite like design variables. I tried to break those up in the study and like look at them one by one and research with these experts. Is this a thing that's okay for an AI to change or not? With the intent of, future AIs then enabling certain types of features and not others in order to try to constrain and provide guardrails that will be acceptable and suitable according to the experts. But people do feel generally very negative about the use of AI in this, but nonetheless, there's a lot of development in the field. So I think, you know, it's coming, people are doing it. I feel like it's going along the same route of like beauty filters on social media. Everyone hates them. We all know that they're causing terrible things for our mental health and our youth, but everybody uses them, right? Like we hate it and we use it at the same time. And that's what's happening with AI more broadly and visualization and otherwise as well. And I think even though a lot of people hate it, there's no stopping it and the development is happening. So I'm trying to create guardrails around, you know, how can we do this the most ethically and accurately as possible. Yes.
I'm gonna ask what one of those guardrails would look like.
That is future work. So this study was kind of just getting the perspectives from experts, and I literally just submitted this a couple weeks ago, so haven't necessarily created the next steps for that. But I mean, essentially they would be, the goal of the paper is to point future visualization AI researchers and like, these are the directions that we should go in and these are the directions that we shouldn't. And I mean, will people go in directions they want to anyway? Like, sure, they might go down that other route, but I'm kind of trying to say, you know, this is okay and this is not. So that is my goal. Yes.
Long time ago, did some work with visualizations and one of the things that was commented about is, for instance, trained database and vertical exaggeration in order to, you know, make things stand out more, and you know how you feel about that. But the other thing was we also added an audio channel, so you know, as you move through you got more of an experience from that. So anyway, what do you think about that? Vertical exaggeration?
So there's a two-part question, repeating it for the people online. One is, how do I feel about things like vertical exaggeration, which happens commonly in visualization, you know, people kind of exaggerating what things look like. The second part was about adding sound to visualizations. So first, on the note of exaggeration, I'm not going to say like that I love it or hate it one way or the other. It kind of depends on the scenario. And I mentioned, you know, earlier in my talk that there are some things that you have to lie about, like, you know, not being able to explain quantum mechanics of a photon to an 8-year-old, or like sometimes exaggeration is necessary if you're trying to show the solar system. You know, if you can't see the sun and a planet at the same time, you need to exaggerate the size so that you can see them all. Is that lying or is that helping? It's a very fuzzy boundary in visualization. And that's something that every visualization designer struggles with every day. Every visualization, you kind of have to make that decision because most things are complex to visualize exactly for that reason, because there isn't a straightforward way of, well, we'll just show it the way it is. Well, many times you can't. So exaggeration can be a necessary evil. Or necessary not evil. I don't know. It is necessary oftentimes. The other question was about adding sound to visualization. I think that's super cool. There's an entire field called data sonification, which I have not done any work with, but there are a lot of people doing that research, and it's super cool, especially for people that are vision impaired. It can be an alternative to visualization or to data visualization for yeah, there's data sonification. 3D printing is kind of another thing in that category that makes it more accessible. So I think as many ways as you can communicate something, it just reinforces it. That's really helpful.
If there's no more questions, thank you so much for your time. Keep an eye out on Meetup for our next meeting.